According to Lorentz model, the Hall coefficient RH of metals is given by RH is equal to -3 by 8 into 1 by Ne, RH is equal to -1 by Ne, RH is equal to 1 by Ne, and 3 pi divided by 8 into 1 by Ne. So now what you're supposed to be careful about is the automatic reflection is to go to this, okay? So what you'll realize is that for metals, okay, this is just an approximation, okay, these two values that you have, okay? The actual value is going to have a coefficient on front of it, okay? So I'm not doing the derivation for you, but you'll be doing this derivation in the third semester, okay? So according to Lorentz model, the Hall coefficient of metals is given by. Okay, so now let's understand what the Hall effect is, okay? So you might have done this experiment, probably a virtual experiment. In my batch, we did this virtual experiment to kind of like find out the Hall coefficient and the density, okay? And so basically what they do is they have some kind of a conductor like this that's going to be here. And what they do is they kind of like, let me just take another color. Okay, so this is your magnetic field, okay, acting in some direction. And there's also a current that is going to be supplied to this. So there's some kind of current, okay, that's being supplied to this. Okay, so we'll put it like that. That's your I. And both of these are perpendicular to each other. So then there is a voltage that is produced, which is perpendicular to both of them, and that can be measured. Okay, so you probably take something like this and you can measure the voltage here. Okay, so which is called the Hall voltage. Okay, so now I'm just stating the formulas here. Okay, so this is what is theoretically written. Okay, so according to the Lorentz model, the Hall coefficient of metals is given by RH is equal to -3 by 8 into 1 by Ne. Okay, now the measured values of the Hall coefficient are close to the values which are given by RH is equal to -1 by Ne. So basically this is going to be your theoretical, and this is basically going to be something that you look at experimentally. Okay, so experimentally the values are going to be coming close to this. This is the actual value that you should be getting. Okay, so how is your RH measured? Basically you take the electric field and divided by the current density and the magnetic field. So that's how your RH is measured when you do the experiment. Okay, so let's move on to the next one. Okay, so I hope you recall some of the superconductivity we discussed, like the squids and things like that, which are based on the Josephson junction. So basically what this is discussing, or what this Josephson junction means, is basically, let's say you have a superconductor here and you have another superconductor here, and then there is going to be some kind of a metal which is placed between them, metal or insulator. Okay, so if it's an insulator, it has to be thinner. Okay, and if it's a metal, it can be thicker. And what you realize is that the Cooper pairs that you had here, right? Remember, so you had an electron and electron. You realize that they kind of like flow past through this barrier, even though it's not superconducting. They kind of like flow past, and then they are going to come here. What you also realize is there's going to be a phase change between this guy, these Cooper pairs and these Cooper pairs. Okay, so that's your basic idea of the Josephson junction. So let's look at what the calculations are really looking at. Okay, so here they've asked you for the frequency of your AC current produced when DC voltage of 15 microvolt is applied across the Josephson junction. So you should probably remember the formula for the frequency of your current. Okay, so the idea here is basically you supply something that is DC and you end up getting AC. Okay, so that's one of the key points here. Okay, so what are Josephson junctions? So Josephson junction is made by sandwiching a thin layer of non-superconducting material between. The Josephson junction is made by sandwiching a thin layer of non-superconducting material between two layers of a superconducting material. Okay, so Brian Josephson predicted that pairs of superconducting electrons could tunnel right through the non-superconducting barrier from one superconductor to another. He also predicted the exact form of the current and voltage relations for this junction. And okay, so this is what I told you about. So it can be your insulator, okay, it can be a dielectric, or it can be another metal. So if it's another metal, it can be thicker. If it's an insulator, it can be it has to be thinner. Now this is a general standard, okay. The frequency of your AC voltage is nearly 500 gigahertz per millivolt across the junction, okay. So this is the general standard. Now where you're supposed to like be careful is, okay, so here this value that you have, so you had a 500 gigahertz per millivolt, okay. So the millivolt is where you're supposed to be focusing at, okay. Now as long as the current is through the junction is less than the critical current, the voltage is zero. As soon as your current exceeds the critical current, then your voltage is not zero, but it starts oscillating in time. So basically what you're doing is you're supplying DC and you're obtaining AC once your DC is above some critical DC value, okay. So that's what's happening here, okay. So now this is how it's defined. I hope you remember this. This is called your superconducting magnetic flux quantum. I think I kind of like told you into how to remember it. So basically you end up having H divided by 2E, right? So that was your superconducting magnetic flux quantum. Now your F of J is equal to V naught. This is very, very important, okay? It has to be in millivolt, okay? That is where you're supposed to be focusing at. Now you realize that none of the answers kind of like match the options, okay. So this was a question that they kind of like gave grace marks for, okay. So all of these are wrong options that were mentioned in the question. Now let's look at this a little more carefully. So you have a V naught in millivolt divided by your magnetic flux quantum, which is constant for every superconductor there is, okay. So H divided by 2E, you take your 2E on top and you calculate it. So now you also realize that if I go back to the question, okay, if you also realize that this is given in microvolt, okay, this is given in microvolts. So you have a 15 microvolt that's present here. So let's move to this, okay. You have a 15 microvolt, so that has to be converted into a millivolt. And how do you do that? You multiply it with 10 to the power of minus 3, okay. So basically, when you say microvolt, it's 10 to the power of when you say millivolt, it's 10 to the power of minus 3. When you say microvolt, it's 10 to the power of minus 6. So you have to reduce it by that factor. Okay, so now the voltage source is DC, but the resulting current is AC. So this is a key point to remember. Okay, so I'll just like underline it so that you kind of like strike it on your mind. This is the whole idea that's there behind your Josephson junctions. Okay, so let's move to this. Okay, so this is quite easy and simple. I think you can do it without thinking much. Okay, but you end up, you know, getting scared when you immediately see something like this. Okay, but I think this is fairly simple because it's done a lot of times in PU. Okay, so the nearest neighbor distance 2 are in a body centered cube, BCC is, okay, so these are the options that are given to you. So you know nothing about your BCC, fine. The thing that you can do is you can draw a cube like this, okay. You can draw a cube like this. So let's draw the cube, okay. Now they've said body centered, so what I'm going to do is I'm going to draw one in the center, okay. So there's one in the center, then there's one at the side, okay, and there's one on this side, okay. So these are going to be actually the same sizes. My figures are not quite to scale, okay. So what you end up having here is, okay, so this is basically passing through okay, so this edge to this edge, okay. So now what you're supposed to remember is if you have a cube, the diagonal from one end to the other end is given by root 3a, okay. So it's given by root 3a, and now what do? You basically have to calculate, take that root 3a and kind of like match it up with the total number of R's that you can find here, okay. So the radii of these atoms or molecules. So what do you end up having here? You end up having 4R is equal to root 3a. Now, what have they given you? They've asked you for the nearest neighbor distance. So when you talk of the nearest neighbor distance, they've given 2 here or here, but if they haven't given it, so you're basically talking about the distance between the centers of 2 atoms. Okay, so let's do that. What is 2r? It's equal to root 3a divided by 2, and that's what you get here, root 3a divided by 2. So that's option C. Okay, so this is the whole calculation, and this is how it's actually supposed to look. Okay, so there's a particle at the center. That's your body center. Okay, so now let's look at this. Now this is a little confusing. Okay, this is confusing because sometimes you really do not know which one to take. Okay, sometimes you end up taking one kind of frequency and sometimes you end up taking another kind of frequency. So there are 2 frequencies which are kind of like similar to each other. Okay, one is your cyclotron frequency, and how do you get that? So I'll just show you how you get your cyclotron frequency. So basically you have something like your centripetal force, which is mv squared divided by r, is equal to, what do you end up having? You have qvb sine theta, right? So that's the force on a charged particle moving in a magnetic field. So let's just take qvb. Okay, so you cancel these 2 out, and then you get mv divided by r is equal to qb. Now the next thing that you do is basically find out r. So you get mv divided by qb. Okay, also, what do you need to find basically? So when you're talking about your cyclotron frequency, okay, I will just write cyclotron here, and you basically have to get 1 by t, right? So what is time basically? Time is equal to distance divided by speed. So I will write this as 1 divided by 2 pi r, okay, and v. Okay, so what do I get here? I substitute this r that I got from here, and I get qb, my v gets cancelled, so you basically get qb divided by m, 2m. Okay, there's a 2 pi here, so 2 pi m. So this is your qb divided by 2 pi m. So if I write it in terms of angular frequency, it's going to be qb divided by m. Okay, so this is your cyclotron frequency. Now, when you look at something called the Larmor precession, what you're going to see is that the Larmor frequency, which is obtained because of the Larmor precession, is going to be 1 by 2 times this. Okay, so let's just look at that. Okay, so those are the answers that are given to you, and this question relates to the Larmor frequency, and let's look at it this way. Okay, so let's read the question first and then move on. A free electron is placed in a magnetic field of strength 1 Tesla. The resonance frequency, okay, is given as what? Okay, so they've given you this G factor, and they've given you the Bohr Magneton. Okay, so now let's move to this. Okay, so the Larmor precession is the precession of the magnetic moment of an object about an external magnetic field. Okay, so let me just draw that for you. Okay, so let's say this is your electron, and this has a magnetic moment in a certain direction. Okay, let's say this is some mu. It also has a magnetic field. Okay, so now this is going to basically precess around this magnetic field. Okay, so it's going to be moving around this magnetic field. Okay, so it's going to go in a circle, like how the top moves. Okay, when you spin the top, it's kind of like going to go in circles around the central axis. Okay, so here it's going to be looking like that. So your magnetic moment basically precesses around the external magnetic field. The objects with the magnetic moment also have an angular momentum and effective internal electric current proportional to the angular momentum. The external magnetic field exerts a torque on the magnetic moment, and this is basically how it looks. So this big arrow is your external magnetic field, and the tiny arrow is like your magnetic moment, which is basically going round and round your external magnetic field. Okay. So the external magnetic field exerts a torque on your magnetic moment. So tau is basically your torque, Okay, and you have a mu cross B. Mu is your magnetic moment and B is your external magnetic field. Okay, so there's something called the gamma, which is called your gyromagnetic ratio, which gives you a proportionality constant between the magnetic moment mu and the angular momentum. Okay, so we'll come to that next. Okay, so the angular momentum J vector precesses about the external field with an angular frequency called the Lama frequency. Okay, so this is equal to omega gamma B, sorry. And then you have your gyromagnetic ratio, which is equal to Eg divided by 2m. So G is basically your G factor. Sometimes it's 1, sometimes it's 2.0, and so on. Okay, so now let's look at what your Bohr Magneton means. So in this question, what they've done is they've actually given you the, let's just go back to the question. Okay, so what they've done here is they've actually given you the Bohr Magneton. Okay, so this is your Bohr Magneton value, and you're supposed to use this value in your calculation, because the thing is that in these kind of exams, they're not going to allow a calculator in. So that you're going to be having to use the values that they give you and kind of like figure it out, rather than using the mass of the electron and then the charge of the electron and making a huge issue with calculations. Okay, so this is how your mu B is. Okay, so the Bohr magneton is the physical constant and the natural unit for representing your magnetic moment of an electron, caused either by its orbital or spin angular momentum. So here you have a mu B, which is equal to E h cross divided by 2me in your SI units. Okay, so now how do we, let's just do the calculation for that. Okay, you have, let's look at this. You have mu B is equal to E h cross divided by 2me. Okay, here you've been given a gamma, which is equal to Eg divided by 2m. So let's take that and put it in your omega. So you have an Eg divided by 2m into B. Okay, now what do? Your mu B, basically you get a divided by h is equal to E divided by 2me. Okay, so what I can do is I can substitute this in terms of the Bohr magneton, because this particle is like an electron. That's what's given in the question. Okay, so you've got a h cross GB into omega. Now the next step that you can do is you got a h cross divided by 2. So let's look at this. So you've got a 2 pi nu. Okay, so I'm going to convert this into linear frequency rather than angular frequency. And then you've got a 2 pi divided by h. This has h cross is like a h cross divided by 2 pi. 2 pi goes on top. You get a mu b g b. So these two get cancelled, and that's what's given here. So your mu is equal to mu b g b divided by h cross. Now you substitute your values and calculate it, you end up getting something like 28.04 gigahertz. Now what is giga? Giga is basically 10 to the power of 9. So I hope you remember all these tiny things that we've learned before. And then you end up getting these values. So let's go back and check what the option is for a minute. Okay, so it's 28.02 gigahertz. Okay, it's option A. Okay, so let's move on to this. This is quite simple. Okay, this is a very simple question. A nucleus has a mass number of 216. Its radius is, so you know how these are related. So basically you have an R is equal to R naught, a to the power of 1 by 3. Now how do you remember this? Okay, so you've got an R naught, which is approximately 1.3 into 10 to the power of minus 15 Fermi. Okay, so minus 15 meters, basically it means it's approximately 1.3 Fermi. Okay, so that's the whole idea. So you do 1.3 into 216 power 1 by 3. Okay, so the cube root of 216 into 1.3. That should give you something like, I think 7.8. Yeah, okay, 7.8 Fermi. So this is you just have to substitute this and then you get the answer for that. Okay, so a couple of other things. So the volume of the nucleus is directly proportional to the total number of nucleons. Okay, and this means that all nuclei basically have your same density. Okay, so that's the general idea. Okay, so this is what you end up having. Okay, so let's look at this. Okay, according to liquid drop model, the surface correction term is proportional to. Okay, so this is something that you will learn in your nuclear physics general paper in the 3rd semester. So I'll just go through it briefly. Okay, there are a lot of nuclear terms that are nuclear concepts that are involved now. So some from the elective paper, some from the general paper. So that I'll try to explain as much as I can, but I suggest you go read it once again. Okay. So according to the nuclear drop model, the surface correction term is proportional to a to the power of 1 by 3, a to the power of 2 by 3, and a to the power of minus 2 by 3. Okay, so there's something called a semi-empirical mass formula. So you can understand what it basically means from this itself. So semi-empirical, some of it was based on the data that was collected while doing experiments, and some of it is based on a theory. Okay, so it's also called the Weizsäcker formula, or the Bethe-Weizsäcker formula, or your Bethe-Weizsäcker mass formula. Okay, so it's used to approximate the mass and a couple of other properties from which you can get the mass. Okay, I mean, a couple of properties from which you can use the mass to calculate them. Okay, so it's from these number of protons and neutrons. Okay, so now let's look at this. Okay, so basically this formula is based on your a theory called your liquid drop model. Okay, it's called the liquid drop model. I think it was given by Gamow, I'm not sure. Okay, so this is the formula which is based on your liquid drop model. Okay, so let's look at the whole idea. So if your mass is given in terms of A and Z, so the atomic mass, okay, of this is given in terms of A and Z, how can you write it now? Okay, so basically you have an M, A comma Z is equal to Z into mH. So mH is basically the mass of the hydrogen, and the other one is your mass of your neutron. Okay, so why hydrogen? Basically the mass of the electron and mass of your proton are basically included in that, so you don't have to end up subtracting just the mass of the electron later on. So that's why they've given this mH. And then you have the binding energy here. Okay, so that's what's given here. Okay, now the binding energy is basically the thing that's expressed in terms of several terms. Okay, so in that you have something called, let's go back to the question. They've given according to your liquid drop model, the surface correction term is proportional to. Okay, so there is one thing called your volume energy. Then there's something called the surface energy. Okay, your Coulomb energy, your asymmetry energy, and then you finally have your pairing energy. So let's just go through what all these terms mean. Okay, you'll be deriving it extensively and using it for several experiments in your nuclear physics course. If you're taking the elective, you end up doing an experiment on this. I mean, it's like a chart experiment. Basically, you have to calculate your binding energy, and then you have to use that and calculate the mass, look at the error from the actual values that were obtained of the binding energy experimentally, and then look at the error that's kind of like that. So that's the whole idea behind that experiment, and you'll only do that if you take the elective. So okay, so let's look at the first term called the volume energy. So here you have an EV, okay, to represent the energy correction due to the volume, is equal to A1A. Okay, so these are basically coefficients. You end up having several coefficients, A1, A2, A3, and so on. Okay, this is the surface energy. So you have an ES is equal to A2, A to the power of 2 by 3. So now you know what the answer is. Okay, so you will end up kind of like equating the surface energy with the volume and kind of like calculating what this entire thing is. Okay, then you have a Coulomb energy, which is minus A3 Z squared divided by A to the power of 1 by 3. And then you have an asymmetry energy, which is EA is equal to minus A4. These are all coefficients. Okay, so these are all the values that are given to you. And then you have an A minus 2Z whole square divided by A. And then you finally have the pairing term. Okay, so it depends on A and Z. And basically, it's 0 for your odd A. Now, if you have an even nuclei, it's positive. And if you have odd nuclei, it's negative. And this is how it's given to you. Okay, so if it's odd A, it's 0. If it's even nuclei, it's positive, and if it's odd nuclei, it's negative. So delta is equal to A5, a to the power of minus 3 by 4. So this is the gist of the whole derivation that was there in the third semester. Okay, so I think this you might be knowing because you've done a set of famous experiments in your experimental techniques in physics, and one of them was parity violation. Okay, so there was an experiment which was done by Wu to kind of like say that parity is violated. Okay, so what they kind of like saw till about say 1956 was that they saw that parity is not violated in your strong interaction and in your electromagnetic interaction. But after that, they kind of like looked and looked, and they could never find an experimental confirmation where your parity is not violated in weak interactions. Weak interactions, let's give an example, say beta decay, okay? So they kind of like saw that it was not it was violated in beta decay, and that was, this experiment was done by Wu, okay? So let's look at this, okay? So I'll just tell you a story, not really going into the mathematics of it. Okay, so parity is violated during strong interaction, weak interaction, electromagnetic interaction, and gravitational interaction. So let's look at this. Okay, so basically it's violated during your weak interaction. All the other interactions, they kind of remain constant. Okay, so parity is not violated there. Okay, they're conserved in the other interactions. So before 1956, it was taken that the laws of physics are invariant under parity, but then Li and Yang realized there were experimental evidences of parity invariance in strong electromagnetic interactions, but there were no experimental confirmations, and I think this is again a typo. Okay, so it should have been weak. Okay, weak interactions. Okay, so let's move on. Okay, so they proposed a test which was done by C.S. Wu. Okay, so it's sad that this lady never got the Nobel Prize. Okay, so Li and Yang ended up getting the Nobel Prize, but then she got another prize eventually. Okay, so now basically they did this. Okay, so the cobalt-60 nuclei were aligned with their spins upwards. So what you end up seeing is basically, okay, I take this spin and then there's something, okay, there's another vector here. Okay, so the spins are basically this direction, and then you put a mirror over here. Okay, and then you realize the spins are like this. Okay, and what happens is your mu ends up being like this. Okay, the electron here was coming out in this way, in this direction, but here what you realize is this is what's happening. Instead of actually getting it up here and this happening, okay, so instead of this happening, this is your mirror image. Okay, so instead of this happening, what they realized was this is basically a mirror image, right? So when you kind of like change the spin, your mu kind of like shifts too. Okay, so this is not what's happening. What's really happening is this. Okay, so this kind of goes down here, and then your electron kind of comes from this same direction. But there is this shift that's going to be happening. So then we realize that parity is not actually conserved in weak interaction. So your cobalt-60 undergoes beta decay, which is your weak interaction, and Wu recorded the direction of the electrons. She found that most of the electrons came out in the direction of spin of the cobalt-60 nuclei. If we examine the mirror image of the same process, the image nucleus rotates in the opposite direction and the spin points downwards. The image electrons must go downwards, but the experimental observation contradicts this. Okay, so it's kind of like going 180. Okay, so basically I will show you another diagram which is much more better than this. So this confirmed that your parity was not violated in weak interaction. So basically this is the beta decay of a nucleus. Okay, the magnetic moment is mu, and it is basically what you're supposed to do is kind of like wrap your hands around this this ball. Okay, basically your fingers are supposed to curve along the direction of the spin. Okay, and then your thumb basically gives you the direction of your mu. Okay, so now this is the way your electron is coming out. Okay, so it's coming out at an angle theta to this direction. Now let's look at another figure where you basically have a mirror image of the whole setup. You realize that the spin is in the opposite direction. Okay, so you realize this guy is opposite to this guy. Okay, and your mu, what happens? Which was on top kind of like fits and comes to the bottom because of this spin shift. And what you realize here is your angle between E and mu is basically 180 minus theta. Okay, so this is the whole thing that told us that parity is actually not conserved. Okay, so if it was such, okay, what you're supposed to be getting is your electrons are supposed to be coming kind of like this direction, but that's not what's happening. This is kind of like moving still upward. So that's the whole idea. Okay, so this is quite simple. The binding energy of two nuclei, N, P, and 2NQ are x joule and y joule respectively. If 2x is greater than y, then the energy released in this reaction, NP, MP is equal to 2NQ is. Okay, so this question has a typo. Okay, nobody challenged it that year, so they ended up getting, kind of like giving marks for it. Okay, so this reaction is actually supposed to be NP plus NP is equal to 2NQ. So this is something that they give in PU questions. Okay, so this is quite easy. What you realize is they've said your 2x is greater than x. These two have your, these two, x and y, are basically the binding energy. So all you have to do is end up subtracting 2x minus y. Okay, so you take your reactants and you subtract it from the product binding energy. Okay, so let's look at this. So you end up getting 2x minus y, that's option C. Okay, so the only idea is this is the corrected equation. Okay, this is the energy released formula. So binding energy of your reactants minus binding energy of the products. So you get x plus x minus y is equal to 2x minus y. So that's pretty simple. Now, this is a question. Okay, so you have to be quite careful in kind of like analyzing this. Okay, so beta decay involves the interaction of leptons with baryonic field, baryons with leptonic field, baryons with electromagnetic field, photons with baryonic field. Okay, so if you look at your beta decays, okay, so basically what's happening is, I think I will try and show you a bit of you know, like these terminologies, what you mean by leptons, baryons, as we go along. Okay, but I don't think I'll be able to cover it because it's such an extensive topic. So I kind of like would like you to read about a couple of things which I'll probably send you after this. Okay, so basically there are like these categories that were kind of like put out by Murray Gell-Mann. Okay, so there is something called the eightfold wave. Okay, so that basically involves kind of like, let's see, how do I put it up? Okay, so there's something called the baryon octet. Okay, baryon octet, and this is basically something to do with the SU3 symmetries and things like that, a lot of group theory that was there. Okay, so there's something called the baryon octet, and I'm going to try and draw it for you. Okay, okay, so let's kind of like draw this. Okay, this is called the 8-dimensional irreducible representation of SU3. Okay, so that's a lot to do with a group theory. Okay, so you got, okay, I will write this. This is your neutron. This is the proton. Okay, this is how it's kind of like drawn. Okay. This is sigma minus. Okay, and then in the middle you kind of like have lambda 0 and sigma 0, and you end up having sigma plus, and here you have your cascade minus and your cascade 0. Okay, so this is the baryon octet. Similarly, there's kind of like something called the baryon decuplet. Okay, and there's also another thing called the meson octet. So the thing is that it's kind of like easy to find out different properties of these particles that you have here. Okay, so the whole idea in beta decay is basically you move from one baryon to another baryon. Either you move from a neutron to a proton, or you move from a proton to a neutron, okay? And basically you end up getting something called the electron or your positron, okay? And you also get your neutrino as well as your anti-neutrino coming up, okay? So these are the ideas behind this beta decay. There's another kind of beta decay which absorbs an electron, and that's called electron capture, and then you end up getting another barrier, okay? So these things, your neutron and proton are basically your baryons. The electrons and the anti-neutrinos are called the leptons. So what are you doing in your beta decay? You're changing from one baryon to another baryon, okay? So this is how I picture it. You're changing from one baryon to another baryon, and then what are you getting as a result of that? Basically you end up having in leptons remaining, right? So this is basically the interaction of your baryons with the leptonic field, okay? So that's how you're supposed to understand it now, okay? Because we haven't really learned, because I'm assuming everybody is in the second semester, so I'm kind of like trying to like make sense of a little stuff, okay? Not just feeding in too much detail, but just a little bit here and there, okay? So I think towards the end of all these papers, you might have like a really great bank of knowledge, and it's going to be really useful for your third semester. Okay, so basically it's going from one baryon to another baryon. So that's why it's an interaction of baryons with the leptonic field, okay? So I've given up beta minus decay and beta plus decay. Let's not look at electron capture for now, okay? So your beta minus decay, basically you have your beta particle or your neutron, it's going to your proton, and then you have an electron. Here you have an electron, and then you have a neutron, which is going to your neutron, and you also have a positron, okay? So along with this, you're going to have neutrino and anti-neutrino emissions. Okay, so this is the whole idea. Okay, so I think I will kind of like send some supporting material on this or something like that. Just remind me after a couple of hours today. Okay, after this session's hour goes. Okay, so let's look at this. So the nucleons prefer, there's a lot of nuclear questions coming up. So little kind of like, if you don't understand, it's fine, okay? Just listen, okay? The nucleons prefer to spend most of their time inside the deuteron boundary, at the origin of the deuteron boundary, at the surface of the deuteron boundary, and outside the deuteron boundary, okay? So I'm going to kind of like diagrammatically explain this to you, okay? So what you kind of like see is the wave function kind of like extends outside the potential well for your deuteron, okay? So we will kind of like look into this, okay? So one of the ways that I think would be logical to explain this is looking at your binding energy per nucleon, okay? So here, basically the constituent of a deuteron is what? You have one proton and you have a one neutron here, okay? And the mass and all these properties are given to you. Let's look at the binding energy, okay? So let's look at this property that we have here. Okay, so let's look at the binding energy, and if you're looking at the binding energy per nucleon, you get something like 1.11. Okay, so this is for both the proton as well as the neutron together, so you end up getting 2.224 and so on. But what is your average binding energy? So this, I think the average binding energy per nucleon is like well remembered. So it's approximately something like 8 MeV per nucleon, okay? So per nucleon. So it's something like this. Now, look at this, okay? So the binding energy here is like quite small compared to your average binding energy. So you realize that not all of the nucleus can actually be kind of stuck inside it, okay? So the nucleons basically prefer to spend their time outside the deuteron boundary, okay? Because of such low amount of your binding energy, they prefer to spend most of their time outside the deuteron boundary. So another way to look at this is, okay, so this is the explanation here. Okay, so another way to look at this is basically a potential well for your bound state of your deuterium, okay? So this is your deuteron wave function, and what you see is there's like this exponential tail, and what you see is like the length between the proton and the neutron is like so long, okay? So most of the wave function is like falling off this region. So you realize that it would probably be, you know, like it would probably prefer to be outside that region, okay, outside the potential of that of the deuterium. Okay, so that's the explanation for that question. Okay, I'm trying to like the thing is that you could try and kind of find out the probability for your particular deuterium wave functions, but it's going to take quite a while to be actually doing that. So let's look at the quickest way to get to the answer, okay, right now. But I think as we progress, I can explain a bit more regarding these concepts, and it will kind of like sink in a lot more. Okay, so let's look at this. The ground state spin of even nuclei is it zero? Is it half integral, negative only, positive only? So what you're supposed to remember is neutrons, protons, electrons, all of them are spin half particles, okay? So just keep remembering them, neutrons, protons, and electrons, all of them are spin half particles. So basically when you combine a neutron and a proton together, you end up getting, you end up getting integral spin, or you end up getting zero spin. Okay, so let's move to the next slide. Okay, so spin and parity of nuclear ground states. Nuclear ground states have intrinsic spin as well as a well-defined parity of eta equal to plus and minus 1, defined by the behavior of wave functions for all the nucleons under the reversal of the coordinates with the center of the nucleus at the boundary. So parity is basically what? If you reverse the coordinates of the wave function, do you get the same wave function? If then your parity is 1. If after reversing the coordinates, do you get a negative of the wave function that you had initially, then your parity is minus 1. Okay, so the spin and parity of your nuclear ground states can be determined from the shell model, which is something that you'll be learning in your third and fourth semesters. Okay, so the protons and neutrons tend to pair up so that the spin of each pair is 0 and each pair has even parity. Okay, so your parity is plus 1. So why is that? Your protons basically have a spin half, neutrons have a spin half, so they kind of like pair up and then they end up getting a spin of 0. Okay, so what is your answer here? Okay, the ground state spin of even nuclei is 0. Okay, so let's look at the different things that are there. So even nuclei both have Z and A even. So you have 0 intrinsic spin or even parity. Why? Because your proton and neutron are like combining, and there are even number of those combinations that are there. Okay, let's look at the next one. You have an odd A nuclei. You have one unpaired nucleon. Okay, in your odd A nuclei, and basically the J value of that unpaired neutron and your parity is basically minus 1 whole power L. Okay, so the spin is equal to the J value and the parity is equal to minus 1 whole power L. So let's just write that down so that it's more clear. Spin is equal to the J value and parity is basically minus 1 whole power L. Okay, your L is the angular orbital momentum, Okay, next let's look at this. Okay, so in the odd nuclei, in this case unpaired proton, okay, whose total angular momentum is J1, and an unpaired neutron whose total angular momentum is J2. So the total spin of the nucleus becomes the vector sum of these two and can take values from J1 minus J2, okay, modulus of J1 minus J2, and to modulus of J1 plus J2 in unit steps. Okay, and then you have the parity given by minus 1 whole power L plus 1 and L plus 2. So these are the different conditions. What you have to remember in this particular question was that you have a Z as even and A as even. So you end up getting 0 intrinsic spin and even parity. Okay, so let's move to the next one. Okay. Okay, so this is again something that you will learn in the elective. Okay, so this is not there in any of the general papers. You're going to be learning about this collective model in your elective. So I see that there are a lot of nuclear questions that are coming up. Okay, so these are all kind of like learned in the elective papers. So if you have a chance to take the nuclear elective, take it. Okay, so it's going to be hard. It's not very easy, but if you have a chance to take the nuclear elective, I think you should take it because most of the questions that are coming up are, like based on this nuclear paper. Okay, so according to the collective rotational model, the spin parity of the lowest energy state is, okay, so these are the values that are given to you. Now I'm going to show you a diagram. This won't make much sense, okay. Also, I will kind of try to tell you about a little bit of the independent particle model later on, right? Not right now, but there's something called the IPM that's written in your slide. So basically, there was independent particle model, and then there was collective model. So basically, we're trying to look at different ways to describe this whole system. Okay, so that's the whole idea. So first there was independent particle model, then you had collective model, and it's going on like that. Okay. So basically it's option D. I will show you a figure. I'm not sure if the spectra will make much sense to you right now, but I will try. Okay, so if you don't understand it, ask me at the end when I give you some time. Okay, so there are two typical low lying energy spectra which are observed experimentally in even nuclei. Okay, so there's a figure that's going to be shown next, so you can compare it with that. Okay, so one is the type 1 spectrum. Okay, which has a 0 plus ground state, a 2 plus excited state at E1, and a triplet of energy levels with spin parity 0 plus, 2 plus, and 4 plus. So now you're going to get confused. Okay, so let's dissect this. Now, these are basically your vibrational energy levels. So you have a 0 plus state, you have a 2 plus state, okay, and then you have 0 plus, 2 plus, 4 plus. Okay, that's how your vibrational spectrum is looking. Okay, I will show you a better figure later on. Okay, the type 2 spectrum is found to exhibit energy levels with E1, which is proportional to I into I plus 1. So I is basically your angular momentum, which is typical of rotational energy levels. Okay, so in the case of your type 2 rotational spectrum, we have E2 divided by E1. Okay, so the ratio, basically you end up getting, there are a couple of questions from GATE on this sector. Okay, so basically what you have is you have to find out the energy E1, or you have to find out the energy E2, or you have to find the ratio of that. Okay, so in your type 1 spectrum, what you see is your energy level is approximately 2. Okay, in your type 2 rotational spectrum, first type 1 is your vibrational spectrum, the type 2 is your rotational spectrum. Okay, so if you remember this relation, it's very handy. Okay, it comes very handy in GATE problems. Okay, so both of these spectra are not arriving from the independent particle model. So I told you what happens. First you had your independent particle model, then you had your collective model. Okay, and then it goes on, there are several other models that come up. Okay, so the independent particle model that you have was not enough. Okay, so that's why they kind of like invented this collective model to kind of like describe systems that you have. Okay, so this is how your vibrational spectrum looks. Okay, so you have a 0 plus state, 2 plus state, and you have 0, 2, 4. Okay, so all of these are basically in your E2 band. Okay, and this is how your rotational spectrum looks. Okay, so you have 0 plus, 2 plus, 4 plus, 6 plus, 8 plus, and so on. Okay, so let's go back to this. Okay, so according to the collective rotational model, the spin parity of the lowest energy state is, you've seen in the diagram, it's a 0 plus, so you end up taking it's a 0 plus for now. Let's not go into the math right now. Okay. Okay, so this is basically talking about why the collective model came into a picture. Okay, so the independent particle model had a lot of shortcomings. Okay, there were a lot of issues, like a couple of issues with Schmidt lines and things like that. Okay, so you won't learn it right now. You'll probably, it's there in the general paper, I think, in your third semester. Okay, so if you want to know more, ask me. Okay, ask me questions if you want to know more about it. I can send you some reading material on that. Okay, so it was suggested by Rainwater, this is a scientist, okay, that there could be collective motion of the nucleus in contrast to extreme independent particle motion. Okay, so such collective model causes deformations in your surface of the nucleus, either permanently or temporarily. This results in structural changes, and hence one finds type of low energy spectra, large electric dipole moments, and all those kinds of properties. There are a lot of terminology here that is really fresh to you. Okay, so just don't get scared. The whole idea is to like kind of like crack these questions. Okay, so right now that's the whole idea. But if you want more material on this, I told you I can give it to you. Okay, so let's look at this. Okay, yeah. Okay, so basically this collective models mathematical things was done by Age Bohr and Ben Muttelson. I think Age Bohr is the grandson of Bohr. I'm not sure. Okay, so I think he's like the grandson, but I'm not very entirely sure right now. Okay, so let's look at this. This basically involves several different. Okay, so basically what happens is when you have beta decay, there are several models or several transitions that can occur in your beta decay. Okay, so let me just show you all the options. So here, basically you end up having a pure Fermi allowed transition. Okay, they're looking at transitions here. This is your Gamma-Teller transition, and then there is a mixed transition where these two Fermi and your Gamma-Teller are kind of like mixed together. And then this is pseudo-scalar, which is none related to none of this. But your Gamma-Teller transition is also called a pseudo-vector transition. So I think they're kind of trying to confuse you, okay, with this scalar terminology coming up into this picture. Okay, so basically when you're looking at your Fermi transitions, your angular momentum does not change, okay, it's going to stay, your delta I is basically going to be 0. Next, when you're looking at this guy, it can change from 0 to plus or minus 1. If you're looking at a mixed state, okay, so here what basically happens is you are kind of like allowed excitations, and the other one you're not allowed excitations. So in your mixed, you end up getting excitations in your resultant nucleus, okay? So you have excitation sometimes, you don't have excitation sometimes. Even though it's the same parent nuclei and the same daughter nuclei and all that, you are allowed to have excitations in one and you're not allowed to have excitations in one. So that's what this mixed kind of deals with. Okay, so that's like the summary of it. Okay, so let's just go through this in detail. A Fermi transition or a Gamma-Teller transition are types of nuclear beta decay determined by change in angular momentum or spin. Okay. In the Fermi transition, the spins of the emitted particles are anti-parallel. Okay, so your S becomes 0. So the angular momentum of the initial and final states are kind of unchanged. So you have delta J is equal to 0. Okay. In contrast to your Fermi transition, for which your delta J is 0, your Gamma-Teller transition basically has delta J equal to 0 and plus or minus 1. Okay. So between the initial and final angular momentum states of the nucleus. So it's basically going from a 0 to a plus 1. Okay, so it's basically going from 0 to either plus 1 state or it's going from 0 to a minus 1 state. Okay, so now let's look at this. The Gamma-Teller transition is a pseudo-vector transition. So that's what I told you. They kind of like trying to trick you with putting in the terms like pseudo-scalar. That is, the selection rules for the beta caused by such transitions involve no parity. Okay, there's no parity here. So it's basically called pseudo-vector transitions. In the other case, you basically have parity coming into the picture. Okay, so that's that. Okay, so let's just move on to mixed Fermi and Gamma-Teller decay. Okay, so there are two possible final states here that can happen. Either it's an excited state or a non-excited state. If you look at the equations, which I kind of like didn't put in, okay, so I really don't want to confuse you, but basically when you look into the equations, you see something like X going to Y star, and then you basically have something like your electron plus your anti-neutrino coming here, okay, neutrino and anti-neutrino coming. And then you have something like X becoming Y plus the same thing happening all over again. So you have something like these mixed transitions, which are giving you, you know, two possible final states happening. Okay, so that's the whole idea of this. Okay, so that's the details on that. Okay, so now, okay, so basically, if you're taking the nuclear elective, okay, you will have to mug up these quark compositions of proton and neutron. Your up quark, down quark, strange quark. Okay, you basically don't have anything here which involves charm quark or things like that, which is like quite, you know, like mugging it up is like one big thing. So what I did was, I remember I wanted to like by heart this whole table, so I ended up making a song on it. Okay, not song exactly, something that kind of like rhymes with it. Okay, so you can try doing something like that. Okay, so the quark compositions of your proton and neutron respectively are, okay, so I will kind of like show you that baryon octet that I kind of drew for you. So you have a neutron, proton, sigma minus, sigma 0, lambda, all that. Okay, you have your cascade coming up. Okay, so here you kind of like see U DD for your neutron and UUD for your proton. Okay, so you end up having this option B. So you have UUD for a proton and DDU for your neutron. Okay, so you'll have to kind of memorize it. Okay, so there's no way out other than that. Okay, there's like, okay, so the thing why it's called octet is basically a 1, 2, 3, 4, 5, 6, 7, 8 particles here. Okay, in your decoplate you end up having 10 particles. Okay, so it's going to basically look like this in your decoplate. Okay, you're going to have particles here. Basically you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's how your decoplate is going to look. And this basically you have the same kind of an octet for mesons also. Okay, so it's probably good to memorize this and keep it before, you know, like keep it with you. Okay, so I don't know if I have the recording of what I did now, but I will try to search for it if I have the recording of that particular thing I made. Okay, so let's look into the next one. Okay, so this is basically something to do with nothing out of your syllabus. Okay, lock-in amplifiers are not there in your syllabus at all. But what I'll tell you what basically it does. So this lock-in amplifier, what it does is it takes a signal, okay, and basically you have another reference signal that's coming up here. So you have an input signal here and you have a reference signal, and they kind of like merge it together. Okay, and they lock in at a particular frequency. Okay, so you get a high peak and then you get a low peak and things like that. So what this basically does is basically when you have to send some kind of information, you also have a carrier wave coming along with it, and then you have certain noise. Okay, so what this lock-in amplifier does is basically it kind of like removes the carrier wave from it. Okay, there's noise, there's carrier wave, and there's information that's passing through. So what the lock-in amplifier does is take away the carrier wave. Okay, so let's look at this. Okay, so this is something that you have to kind of like mug up. Okay, you can't derive it right now. Okay, so the best thing is to just, okay, there are going to be questions where you really can't do anything much. Okay, the syllabus is so vast that you really can't analyze much of it. So the only thing you can do is learn that particular question and go on. Okay, so in a lock-in amplifier, you can extract a signal called a carrier wave from an extremely noisy environment. Okay, the lock-in amplifier is responsible for extracting the AC signal which carries information. What does the lock-in amplifier do? It takes the incoming signal, okay, and it kind of like multiplies it with a pure sine wave, okay, and it's matched to a particular frequency, okay, called the omega L, which I will be talking about in the next point. Okay, so the frequency of this signal driving the experiment is basically omega R. Okay. So the resulting signal will have components at both omega R plus L and omega R minus L. Okay, so where the omega L is the lock-in frequency. If your omega R is matched to your omega L, the difference signal will be a DC signal. Okay, so basically you are kind of like getting, your output is a DC signal that you're getting. Okay, so your initial tendency is to kind of like take this part, okay, DC part of the signal, but let's read a little more. Okay, so if your omega L is matched to omega L, the difference will be DC. After the narrow low pass filtering, this DC signal is proportional to the original AC signal will be all that remains. Okay, so you only have a DC signal that's remaining in your output. So I've done a couple of derivations. I've just taken the result of that. So the DC output of the lock-in is proportional to di by dV, okay, as desired. So let's look at this. Okay, so if you do not know anything, the first thing that you're supposed to do is look into what they're looking at. Typical current voltage characteristic. Okay, so usually what they do is they end up taking an I versus V. Okay, they're looking at current voltage characteristics, so you should know that it's something that's related to your I and V. Okay, so that's one way you could kind of like decide its like it's looking at your change in your I to the change in V. Okay, if you know nothing about lock-in amplifiers, that's one way you can look into it. Okay, so I think this is it. Okay, we've kind of like finished the 2013 paper, except for one electronics question that's still pending on counters. What I will do is I will make a short video on it and I will put it across to you. I will upload it on YouTube because I think that's the most convenient way to access stuff. So I will take some time, just do that question, just discuss a little bit about counters. A 5-minute video should be sufficient for that problem.